So, today we are going to discuss principle of yarn formation. Now, let us look at this slide. The stages of yarn formation is stated here. The first stage is deposition of separated fibers in the rotor groove. So, we have already discussed that once this fiber is fed, there is a opening roller which will separate the fibers and then feed them into the rotor. So, separated fibers are actually landing on the wall of the rotor, and from there they move towards the rotor groove. Now, once they are settled there, the next stage will be consolidation of these separated fibers. So, consolidation will see that they are basically due to the centrifugal force which will be acting on the fibers. So, these consolidated fibers are now twisted by the rotor. So, rotor is the twisting element in the case of rotor spinning, and we will see also how the rotor actually twist into the bundle of fibers. So, once the twist is inserted into the fibers, the job that is left now is simply withdrawal, that we need to remove the twisted fibers from the rotor and then wind the yarn onto a package. So, we will see how the yarn is wound onto a package later on. However, the yarn formation can be seen as if it consists of three separate stages of operations: deposition of fibers, consolidation of fibers, followed by twisting and withdrawal. The fiber deposition process is very interesting, and we should look into it carefully. Now, in the diagram, what we see here, a circle. The circle represents the rotor groove, and within the circle represented by the black line, very firm black line, which is the rotor, you see another thin line that is basically indicating the deposited fibers which are there in the rotor groove. So, fibers are deposited in the form of layers after layers into the groove. The fiber entry point is shown here. E indicates the fiber entry point in this case. The process of fiber deposition continues as the rotor rotates and fibers are continuously fed, and this will continue till the seed yarn is introduced into the rotor. When you want to spin the yarn, we have to have a bit of already formed yarn with us, which we will feed through the feed tube, and the yarn end will be sucked. It will go inside the rotor, and from there this yarn end will reach the point shown as here P, that is, they will be coming into contact with the deposited fibers which are there. So, the feeding point of the fibers is E. So, as soon as you start feed, the operation starts, the layers start building up. At the same time, we feed a yarn, and the yarn end comes into contact with the fibers which are deposited in the groove. The deposited fibers initially will have a uniform thickness, Now, as soon as the end reaches the deposited layer, it will get attached to it, because the rotor is rotating and the yarn has started getting twisted, or it is receiving torque. So, what will happen? The end of the yarn, which is in contact with the fibers in the rotor groove, that is the point P, it will get entangled with the existing fibers which are there, and it will be, you can say that the yarn end which we have fed will somehow get tied up with the fibers which are already there, and hence a joint gets built up, and now we start pulling the yarn out. That is the stages what happens. Now, let us say that as soon as we start pulling the yarn out after feeding the seed yarn, what happens? There are three things happens now. One is the original ring of fibers is progressively peeled off. Fibers are already there, because before we feed the seed yarn end, we have already started actually feeding the material. That is, there is little time gap between these two. We must feed the fibers first, and then only we will feed the seed yarn. So, the seed yarn end must see the fibers existing in the rotor groove. If there is nothing there, the seed yarn end will not be able to get entangled with the fibers. So, first we feed the fibers and then we feed the seed yarn end. So, once we start pulling the yarn out, the original fiber ring which is there, which will be peeled off gradually, and now onwards more new fiber layers will be deposited simultaneously, because feeding is happening continuously. The new layers start progressively peeled off. So, one is the original fiber ring which was existing before we fed the seed yarn, and now onwards a new layers of fibers will start building up. So, there is a distinction between these two. One is the original fiber ring which is uniform in thickness, and once the yarn we start pulling the yarn out, new layers will start building up, and we will see what is the difference between these two. Stable condition is established when the original fiber ring is completely removed, and we will have a layers of fibers within the rotor, but we will find that the thickness of the layer is not uniform. It will be tapered. Why it will be tapered? That is what we are going to discuss. In the stable conditions, the rate of arrival of fibers should be equal to the rate of withdrawal of the yarn mass, because we are trying to pull the yarn out, at the same time I am feeding the fibers from the sliver. So, that has to be a mass balance. So, rate of feeding of fibers and rate of taking out the fibers in the form of yarn must be same. Now, we will analyze this one, analysis of fiber deposition process. Look at the diagram on the left hand side first. Let us concentrate on that. What is written here? That P is the yarn formation point. So, this is the point where P is there. At the beginning, P is a point on the in the rotor groove, and we can say this is the point where fibers are just getting transformed from a parallel array to a twisted bundle. We call it yarn formation point. Then O is the position of the navel. This is the position of the navel. OP is the yarn arm shown by the blue color. Takeoff nozzle is there, we call it actually navel, which is at the center point of the rotor. From there to the groove of the rotor, the yarn that exists, we call it yarn arm. So, OP is the yarn arm. A is an reference point on the rotor. E is the fiber entry point, because you know that we have already discussed this. The separated fibers are fed through a fiber feed duct or a transport channel. So, the transport channel end say is E. L0 is the first fiber layer which is going to be built up. It is not yet there, it will be there. N is the rotor speed and Na is the yarn arm speed. And what is written here? Na is greater than N. That is, the speed of the yarn arm OP is greater than the speed of the rotor. And Na minus N, that become the relative speed of the arm with respect to rotor. And as soon as the yarn arm OP starts rotating, why does it rotate? Because we pull the yarn out. If we do not pull the yarn out, then the yarn formation point speed and the speed of the rotor will be exactly same. But the moment we start pulling the yarn out, the speed of rotational speed of the yarn arm, which is OP, will be greater than the rotational speed of the rotor, because I am pulling the yarn out. So, the P point with respect to the rotor will keep traveling along the periphery of the rotor. So, Na is always greater than N, and the difference between these two is the relative speed of the arm with respect to rotor. Like speed of the spindle in a ring frame is different from the speed of the traveler. There is a difference between the speed of these two. Similarly, here also there is a speed difference. Okay. Now, we want to visualize what happens after one complete revolution of the yarn arm, that is OP. So, what it is shown here in this diagram, you look that OP is here, this is my OP, P point has come over there, OP is here, it has made, OP has made one revolution. Where the point A will be, A is the reference point on the rotor wall. So, A is moving at the speed of rotor, but P is moving at the speed which is higher than rotor. So, P is always moving ahead of A, and therefore, when P makes one complete revolution, A will be behind P. And what is the gap between these two? That is what is shown here, that when one revolution of the yarn arm OP is equal to N by N A revolution of the rotor, because N a revolution of the yarn arm is equal to N revolution of the rotor. Since N A is greater than N, the points A or L0, L0 is the starting point of the new layer, which is L0. L stands for layer and 0 is the very fast layer. So, they will lag behind P how much? 1 minus N by Na, and that is Na minus N by Na. That is what is shown here. It is from here to there. This is the lag in terms of revolution. So, point A is lagging behind point P by how much? N A minus N by N A revolution. Okay. Let us go to the next slide now. One complete revolution of the rotor, that diagram is shown here. We want to see once the rotor makes one revolution, how the picture looks like. So, when A has reached here, where is P? P must have gone ahead of A. So, P is somewhere here as shown in the diagram. So, A is here, P is there. Now, the moment, first of all try to find out how far P will be ahead of A. So, N revolution of the rotor is N A revolution of the yarn arm. So, they are revolution per minute or revolution per second, whatever we can imagine. So many revolution per unit time. Unit time could be second or minute, it does not matter. So, one revolution of the rotor is capital N A by N revolution of the yarn arm, and therefore, P moves ahead of A by how much? The difference between these two, N A by N minus 1, because one revolution of the rotor. So, that basically means it is capital N A minus N by N revolution. So, that means this whole from here to there, which is not shown, this rotation is N A minus N by N revolution. As OP crosses the fiber entry point, the moment it crossed, like this is the previous diagram. So, from here we are going there, when P was here and then start going moving, a new layer start building up behind P, and that is the layer L1 now. L0 was the previous layer, now L1 has started building up, because just behind P you see there is an empty space, there is no fiber there, because all these fibers have been removed, or these fibers have been transformed into a yarn and then they have been pulled out. So, the moment P crosses this point, that is the fiber entry point E, which is here, a new layer starts building up, that is the layer which is L1. So, we are showing the layer L1 by orange color. Now, how far will be L1 front end from A, or A is the point, the reference point on the rotor, A has made one complete revolution. This will be exactly equal to how far A was behind P when P made one revolution. Therefore, this distance and this distance are exactly same, they will be exactly same, they will not be different from each other. So, we have found out that as OP crosses fiber entry point, a new layer L1 starts building up. The leading end of the new layer L1 moves by how much? N A minus N by N A, that is this value, what is shown here. So, the gap between P and L1, now we are interested to know this gap, P and L1, this gap, this is what we are interested to know. This will be the total, is this value from here to there minus this one. The total is how much? P is ahead of A by this, and L1 is ahead of A is by this value. So, difference between these two will give me the gap between L1 and P, and that is what has been done here. If I do this subtraction, we get a figure N A minus N whole square by N A into N. So, that is the gap between P and L1. So, a small gap is created P and L1. P is moving forward. As P moving forward, it is removing the original fiber ring it is removing fibers from the layer L0 also. Now, it is rotating further and further, and we will see what happens when it makes 2 complete revolutions. After 2 complete revolutions of the rotor, P moved ahead of A is what is shown here, can be is from here to there, and this value is going to be 2 into N A minus N by N. The gap between P and L2 after 2 revolution of the rotor could be 2 into N A minus N whole square by N A into N. See, 2 revolution of the rotor diagram is shown here. This is for the 1 revolution from here we are going there actually. So, now P is here, and when P crossed the point E, another layer started building up, which is shown by the green color. So, every time P is crossing point E, a new layer starts getting formed. So, we had original fiber ring, then the very first layer L0, the second layer L1, now the third layer has started building up, and that is shown by the green color. So, the gap between P and L2 is this. What was the previous figure? When it made 1 complete revolution, it is just double of that. And the distance between the leading ends of successive fiber layers, you see from L0 to L1, L1 to L2, all these distances are N A minus N by N A. They will be all constant. So, that means we are building layers after layers, layers are falling on each other, but there is a shift between the ends. And how much is the shift? The shift is equivalent to capital N A minus N by N A revolution. That will be the distance between successive layers. And this process will continue till the original fiber ring is completely removed, and then we will have layers of fibers formed one after the other, and how they will look like we will come to that. First, number of rotor revolution in one cycle will be, that is till the entire initial fiber ring is taken up or withdrawn. That is going to be time taken by the yarn arm to make one complete traverse along the rotor groove multiplied by the rotor speed. See, point is both the rotor as well as the yarn formation point P, both are moving together simultaneously, and their relative speed is N A minus small n, capital N, and therefore, a bit of fiber layer is transformed into a yarn, and then that is removed. And therefore, it goes on for several cycles, several rotation of the rotor, till the entire fiber ring which was deposited right at the beginning, that is before the seed yarn was introduced, that layer will be completely removed after this many revolution of the rotors. So, we call it the rotor revolution in one cycle, that is time taken by the yarn arm to make one complete traverse along the rotor groove, which is going to be this much, multiplied in this time how many revolution the rotor is going to make, multiplied by n. So, this is the number of revolutions of the rotor in one cycle. and the maximum gap behind P is the gap created in one revolution of the rotor multiplied by number of rotor revolution in one cycle. So, if we see the previous diagram, the slides, we will find that this was what was the gap, that multiplied by number of revolution the rotor takes to complete the cycle is this, and if we multiply these two, we get the figure which is Na minus n by Na. This expression will give you in terms of revolution what is the maximum gap behind P, that is from here to there, this gap, when I have removed all the original fiber ring. And now onwards, the layers of fibers which will be existing within the rotor will look like this. That is, if this is the yarn formation point P, then you see these are the layers lying one on the top of the other, and there is a phase lag between them. So, the maximum length of the layer is be close to this rotor circumference, almost little less depending upon what is this gap. So, actually this will be from here to there, from here to there, that is the length of the layer, first layer, second layer, third layer, they will be one after the other in this way, and as I am putting twist at the point of information P, this parallel layer of fibers is transformed into a twisted bundle of fibers, and that is what is continuously withdrawn. Therefore, what we will expect, that when the stable spinning is going on within the rotor, the fibers are deposited in the form of layers, but this layer thickness is tapered, it is not uniform. It is maximum where the yarn at the yarn formation point, and from there onwards the thickness will reduce. Now, we will take an example to calculate whatever we have discussed. Let us say there is a rotor which is running at 60,000 rpm. The delivery rate of the yarn is 100 meters per minute. Calculate displacement of each layer. Rotor diameter is given 4 centimeter. Also calculate speed of the yarn arm, number of revolution of the rotor in one cycle, and also displacement between successive layers. And if we want to solve this, first of all, if we want to know what is the speed of the yarn arm, speed of the yarn arm will be whatever is the speed of the rotor plus this value, that is the yarn withdrawal rate or delivery rate, which is 100 meters per minute. We multiplied by another 100 to make it centimeters per minute, and then divided it by the circumference of the rotor, which is pi into 4, and that gives you a figure 795. Total is 60,795, that is the actual speed of the yarn arm. But if a person is sitting within the rotor and watching the yarn arm rotating around him, he will find the speed to be 795 rpm, because then the observer himself is also rotating at the speed of 60,000. But from outside frame, the yarn arm speed is going to be 60,795 revolution per minute. Then number of revolution of the rotor in one cycle, we straightway take this formula and substitute the values. We already know the speed of rotor n, speed of yarn arm. So, you can find out that just 75 revolution of the rotor, entire original fibre ring will be removed. So, when the original fibre ring is actually removed, the yarn is thicker. So, that part of the yarn is not really very uniform yarn. But in 75 revolution of the rotor, how much yarn you are taking up? We can also calculate that what is the length of that yarn, which is very little, and therefore, it is insignificant for all practical purpose. But whenever there is a breakage of the yarn and we start the process, there is going to create, there will be a thick place which will be created. So, every rotor break means as soon as we start the operation again, we feed the fibre first and then feed the seed yarn, and therefore, the seed yarn end joins the fibre ring which is already formed, and that ring is of uniform thickness, but that thickness is not equal to the thickness of the yarn that we want to make. It may be more, it may be less, depending upon what is the delay time between these two, or what is the difference. Anyway, so therefore, there is a chance of creation of a fault. So, number of revolution of the rotor in one cycle is 75. Then displacement of each layer also, this is the formula. So, again we substitute, this is equivalent to 0.013 revolutions, and that if we want to know in terms of linear length, we multiply it by pi into d, rotor diameter, and that gives you a figure 1.63 mm. That is, each layer is behind the previous layer by how much? By only 1.63 mm. That is the difference between the layer ends, which is very, very little. Now, fibre deposition within the rotor. See, this is the rotor that is shown here. This is the fibre feed tube. So, these are the fibres which we are feeding from the feed tube, and the fibres are landing directly on the wall of the rotor. So, fibres flowing through the transport channel or feed tube, meaning the same, land on the inclined rotor wall, and then they slip into the rotor groove. Because of what? Why do they slip? They slip because of the centrifugal force. One component of the centrifugal force will cause the fibers to move down, and therefore, this is the rotor wall has to be inclined, otherwise the fibers will not reach the groove easily. Now, when the fibers are released on the rotor wall, there is important conditions that needs to be met. Velocity of rotor wall must be more than the velocity of the incoming fibers. Why? This is to avoid the buckling of the fibers. If the fiber approaches the wall at a higher velocity, then the fiber end will buckle, because end is trying to land on the wall which is moving slowly. So, there will be deceleration, and due to this the fibers are going to buckle. Therefore, this is a very important conditions in the practical field also, that we cannot arbitrarily choose the rotor speed rotor diameter. We have to keep in mind that the way the rotor machine has been designed, at what velocity the fibers are approaching the rotor wall, and this velocity, whatever it is, should be less than the velocity of the rotor wall. And therefore, the ratio of these two, we call it sliding draft, which is typically may vary between 1.5 to 2.5. So, velocity of the rotor wall will depend upon the rotational speed of the rotor and the diameter of the rotor. So, we have to therefore make sure that the rotor runs at a speed, so that the velocity of it is more than the velocity of the approaching fibers. Otherwise, fibers will get buckled, they will be deformed, and then they will settle in the groove, and they will be going to be end break very soon. The yarn quality will suffer. So, there is a lower limit of rotor speed therefore. The air flow within the rotor should not create turbulence. This is also important. The uniform flow depends upon the distance between the feed tube and the rotor wall and the rotor groove. So, all these things are important. This distance from here to there, they are all important. Within the rotor, because the rotor is through rotor we are actually sucking air, and the rotor itself is also generating air current because it is rotating. So, the air within the rotor rotates, at the same time we are also trying to suck air. The whole rotor housing is placed within a negative pressure chamber. Then only through the feed tube the fibers will flow, otherwise how the fibers will move? They can only move if there is a air is sucked, air is made to pass through the feed tube. That means, this whole thing assembly of feed tube, the rotor must be connected to some suction. So, turbulence is a great source of disorientation of fibers in the rotor, in the rotor yarns. So, that aspect needs to be taken care of while designing the entire rotor spin box and also the parameters of the process, especially the suction pressure, the speed of the rotor, the angle through which the feed tube is positioned. All of them will matter. Now, analysis of fiber sliding, as I said, the fibers are going down because of centrifugal force, and how much is the centrifugal force? We all know basic physics. Centrifugal force is mr r omega square. So, mr omega is how much? 2 pi nr. Nr is the speed of the rotor. So, due to this, if this is the F centrifugal force, then it has two components, one is perpendicular and the other is towards the base. Is F sin alpha is forcing the fibers to go down and down, and it will finally reach where? It will reach the rotor groove where the diameter is maximum. So, you want the fibers to be deposited in the groove and remain compressed there. Like in ring spinning, the fibers are held by the pressure between the top and front rollers that holds the fibers together, and then that is twisted. Here it is the air, it is the centrifugal force which is holding the fibers against the wall of the rotor, and then only they are getting transformed into a twisted yarn. With respect to the fiber mass, F by mg is typically 100,000. So, you can imagine that the kind of pressure which is acting on the fibers, very high centrifugal force will be acting on them. So, we can substitute the values and find it out how much it is. For smooth sliding, F sin alpha has to be greater than mu cos alpha. So, mu cos alpha is what? Is the frictional resistance to sliding, or mu is the coefficient of friction between the rotor wall and the fibers. So, this condition has to be met, so that the fibers can go down, and this gives you the conditions that tan alpha should be greater than mu. So, the mu value depends upon the type of fiber that we process and the type of finish that has been given to the inner wall of the rotor. That decides the value of mu. And tan alpha, the alpha value has to be chosen in such a way that tan of alpha is greater than mu, or if I know the value of mu, I can find out what should be the value of alpha, that is the inclination angle of the inner rotor wall. Now, we come to another concept called back doubling. The doubling word is familiar to most of you. We have learned the word doubling from the time you have learned draw frames, where slivers are doubled together. So, several slivers are put together one after the other, and we double it, call it is a doubling operations, and there we do it in order to improve the regularity of the sliver. So, doubling in a way improves regularity. So, doubling is also happening within the rotor, because layers after layers are falling on each other, and therefore, there is a doubling action also. So, this doubling action in a way will improve the uniformity of the layers of fibers which are there, the uniformity of the mass per unit length of the yarn. So, more doubling, better it is always. So, since the fibers are fed continuously through the transport channel, every revolution of the rotor will create one layer. Velocity of the yarn formation point within the rotor is equal to velocity of the yarn withdrawal, that is W. And W, from W we will see we can calculate what should be the rotational speed of the yarn formation point. The yarn formation point within the rotor rotates along the periphery of the rotor as the yarn is withdrawn. Time taken by the yarn formation point to cover the rotor circumference is going to be how much? Pi dr by W. Okay. So much time it will take. If that is the time it takes, then number of revolution of the rotor in this time t is how much? T into nr, or nr is the speed of the rotor. So, every revolution of the rotor makes one layer. So, so many revolutions in time t, same will be the number of layers that will be formed. So, T into nr is going to be the number of layers formed. If T is pi dr by V, so it is pi dr into nr by V, that is the number of layers. And what is nr by V? nr by V is the twist. nr is the rotational speed of the rotor. Rotor is a twister like spindle in the case of ring spinning. So, every revolution of the rotor means one twist is generated. So, nr divided by V, V is the withdrawal rate. So, this part from this part is actually T. So, pi drt is the number of layers which are formed and that many layers will then get transformed into a yarn. So, back doubling formula is therefore becomes pi drt or pi dt, whatever way we want to say. So, where d or in this case small dr is the rotor diameter, T is the twist. So, unit has to be similar. If I write diameter in inches, the twist has to be then turns per inch. If I write diameter in meter, then twist has to be turns per meter. So, the unit has to be same, and multiplication of diameter and twist and pi will give you the back doubling. So, back doubling therefore depends upon how much twist you are keeping into the rotor and what is the diameter of the rotor. So, larger diameter means more back doubling, and therefore, you can say more uniform could be the yarn. Now, the next topic is twist insertion. So, after twisting only the yarn is formed. So, rotor acts as a twister, twisting device. So, twisting process we will discuss now, and here is the diagram, a simple sketch of the rotor and the yarn. These two are the take up rollers, these are all shown here. Now, how the yarn twist is generated? As rotor rotates, the yarn end B is fixed and the arm AP, not BP, the arm AP turns like a crank. Look at this arm AP, this arm AP. The P end is turning because P end is attached to the rotor wall, and that end is turning around the axis of the rotor. And as we turn that end P, the twist is generated in the region AB. And twist starts accumulating there in the region AB. When sufficient twist has been generated, the torque overcomes the resistance to the flow at the bend A. So, here the yarn bends. So, there is a curvature and the yarn at the bending point, the yarn is contact with a metallic surface. So, any contact is a source of frictional resistance to the flow of torque also. and unless there is sufficient twist in the region AB, the torque will not be able to overcome the resistance at the point A where the bend exists. So, when sufficient twist is there, it will now overcome the resistance, and then only the twist will flow from A to P. So, the orange line shows the twist flow directions, whereas the blue line shows the yarn flow directions. So, yarn as it is formed is going out of the rotor, twist is generated in the region AB, and then from A to P it is continuously flowing. At the P point, whatever torque is available or flows there, it picks up the fibers, because it is in contact with the separated fibers which are lying there. So, it will take those fibers and also twist them. So, twist flow in the region AP region, and from there it will go to region P. From P point is here, P to it will now flow a little bit along the periphery of the rotor. Let us say it can go flow up to the point E. After that, the fibers that is shown it here, all blue lines, their parallel array of fibers. So, the twisting torque flows from point P to a certain distance along the periphery. Let us say that distance goes up to E, then P to E is a region where the fibers are partially twisted, and we call it peripheral twist extent, that is PTE, peripheral twist extent. So, twist will flow to certain length, beyond that it cannot flow, because that much torque is not there, and we do not need also. So, twist will be gradually less and less inclination angle and ultimately become parallel fibers, because within the group there is a lot of frictional resistance to the flow of torque, because fibers are pressed with very high centrifugal force. So, the torque has to overcome that also. So, it flows up to a certain distance, or not over the entire periphery of the rotor. Low twist in the PE region may not allow continuous twisting of the fiber pressed against the rotor wall, especially at high rotor speed. The false twist generated at the navel enhances twist in the AP. We will discuss about this part now, that is the false twist generation at the point A. We will see the next slides, we will discuss it in more details. So, for the time being, if we do not consider the false twist part, so what we have learned, that every revolution of the yarn arm AP generates one turn of twist. The twist is initially built up and accumulates in the region AB, and once the sufficient twist accumulates there, the torque will flow to the point P, which it will be able to overcome the resistance at the point A, because of the contact point. If there is a bend, there is too much of pressure also. So, there is a lot of frictional resistance to the twist flow, and then from P, part of the torque also flows along the periphery of the fibers which are there in the rotor groove. So, torque flow from top to bottom, or yarn flow is as is shown in the diagram from bottom to top. Okay. So, we will stop it here today. We will see that there are other aspects also of twist, because twisting is something in the rotor which we try to enhance by some other means. The reason is that we want to basically increase the production speed. So, we generate false twist. So, we all know that false twist is something which is false in nature. That means, it will not affect the final twist in the yarn. There is a temporary change in the twist level within the rotor. We will discuss that. Okay. Thank you.